السلام عليكم دكتور.
عليكم السلام ورحمة الله وبركاته. صباحكم بخير شباب، كيف حال؟
صبحك الله بالنور. دكتور متى بنبدأ الاختبار؟
حيبتدي في الجزء الثاني من الكلاس إن شاء الله.
تمام.
يعني we'll go through اللي هو الجزء اللي يخص السنجل ميكانيكال فيبر كومبريشن سيستم، وبعد كده بس الديمونستريشن للسيستم، وهنخلي الاكزامبل المرة الجاية إن شاء الله.
إن شاء الله.
السلام عليكم، صباح الخير.
عليكم السلام ورحمة الله وبركاته.
Shall we turn on the camera right now or?
No, you should turn it on once we start the quiz, inshallah.
Okay, so may I use my computer until we start the quiz, and then I turn to my phone so that I can.
Yes, you can, no problem. Sure.
Thank you, sir.
I'm just waiting for 1 more minute until probably more would join us.
دكتور.
Yes.
Can you upload the remaining video for the lecture? I mean the previous lecture.
Oh yes, of course, I will do that, حاضر إن شاء الله.
And also if you can post the solution for homework 1 and homework 2. You know, we don't have resources for this course. I mean,
the point is, I was planning to post the homework of solution of homework number 2 yesterday. I have prepared it, but the problem I found that 5 persons did not submit the homework. بدش أضيع عليهم الفرصة إن أنا if I submit the homework then I'm not accepting any homework submission. So this is only just why I waited, but I'll post it today inshallah. It's ready.
Okay, thank you.
طيب معلش يا دكتور، اليوم حنتكلم عن تفاصيل الميد تيرم.
هنتكلم عن إذا كان if it's only about what should we include. Yes we can.
لأنه ما حددنا إلى الآن الوقت بالضبط يعني.
And even start by it. Yeah. It is supposed to be a week from today, if I'm not mistaken. So it is going to include. I'm going to release the second homework today, and let's not include the part that we are covering today. So it will be up to from the start up to the single effect evaporation with thermal vapor compression.
اوكي. طيب الوقت بالضبط يعني حنبدأ الساعة كم مثلا؟
This is what we need if still not all of you are here, because I would prefer that we do it over like 1.5 hours, which we might not be able to afford it in the morning. So probably we may need to do it in the evening. So maybe we can agree upon a time where we can where this can be used, or we can start it in.
Okay. It's before the quiz it will be better because all students will
Yes, I mean once all of you are here, maybe we can just talk about it then, inshallah.
Okay, thank you.
Yeah, you're welcome. Okay, so just to get started, Today we'll be talking about single effect mechanical vapor compression. So there's something unique about this technology, which is we are basically talking about a single effect evaporation system. And as you have seen previously in single effect evaporation system, we are using steam or vapor to preheat the feed, number one, which is the feed seawater. We increase its temperature from T feed to the saturation temperature. Then we evaporate part of it. We take the vapor to condense it in a condenser. And the condenser is also a feed preheater. We use the condenser, the latent heat of the condensing vapor that we extract at the end as a product. We make use of it to preheat the seawater from T cooling water to TF. And accordingly, we are recovering part of the energy that is spent in the unit. The system that we have today is some sort of a modification, a unique system that can be used as a standalone unit, which means that you don't need an external boiler, you don't need a power plant to connect it. And this is a very good option because it's not always that you need electricity and water. Sometimes you need only water and you already have your electric power available. Or it might not be an electric power because here, as it appears from the title, it's a mechanical vapor compression unit. So we're talking about a compressor which runs mechanically. So what you need is just mechanical power input. The mechanical power input can be given by electricity, for example. You can have a compressor that runs with electric power, or you can have the compressor connected to a diesel engine if you are talking about a remote area where no grid is there. So a diesel engine can operate the unit and then you have your desalination system operating. Or if you are in a location with good wind potential, then you can have wind turbines, and the wind turbines can either they can be coupled to the compressor through gears and run it, or the wind turbines can generate electricity and you take the electric power and run the unit. So we're talking about different possibilities that are there. All of them are serving the main idea, which is it can operate as a standalone unit. I have to tell you that the size for these units is so far in the moderate size. It is not very large sizes. It cannot produce hundreds of thousands of cubic meter per day because it's not designed to that. It is designed to operate some sort of a moderate sort of an production, which is something like 5,000 cubic meter per day, which is not a small quantity when you look at it as maybe it's suitable for a small community or so. So some of the benefits have just been stated, and I'm talking about a stand-alone unit, and the units are shown here. Look at the lower units as they appear in the graph. The lower right unit is what's being produced by Alfa Laval. Alfa Laval is one of the biggest heat exchanger companies throughout the world. And as you have seen, what we have basically in these units is heat exchangers. Be it we're talking about an evaporator or feed preheaters, they are basically heat exchangers. So as you can see it here, it's you can look like or it looks like something that rotates the compressor. This thing could be as a diesel engine, or it can be as electric motor working by electric power to run the compressor, and the compressor operates the units. When we look at a little bit of the details of the unit, what we have a mechanical vapor compressor, we have an evaporator, we have a couple of heat exchangers. Why the heat exchangers? Again, because we need the seawater which is brought from the sea to be preheated. So two heat exchangers, one of them is going to use the rejected brine, which is basically hot, to preheat the seawater. The other heat exchanger is making use of the distillate the sweet water that we are producing, which is also hot, to preheat the seawater. So the seawater is being branched into two streams, one of them in a heat exchanger to be heated by the rejected brine, the other one in another heat exchanger to be preheated by the distillate, and then the two streams are connected together to enter into the unit and be sprayed in. Definitely we'll need pumps. We'll need a pump to bring the seawater from the sea, another pump to push the distillate, the fresh water into the distillate tank, and some venting system to get rid of the non-condensable gases. Further, this is a sketch of the unit. And what you may see once you have a first look at the unit is that we do not have a separate condenser. There's no condenser here. There are a couple of heat exchangers. When you see here, this is one heat exchanger, which is basically using the distillate water, and it is made use of to preheat the feed. This is the seawater coming from the sea that is being divided. Part of it will get into a heat exchanger, and the rest is going to go to another heat exchanger. So in that heat exchanger, we are making use of the rejected brine to give energy to the cold seawater so that we preheat the seawater. The second heat exchanger, we are taking the condensate, and the condensate or the condensing vapor, which is the product that we have, is basically used to preheat the feed here. And then the two streams of the seawater, after being heated from tea cooling water to tea feed, are being taken and sprayed into the evaporator. When they are sprayed in the evaporator, part of it is going to be, all of it will be heated to the saturation temperature, TB, and part is going to evaporate. You take the vapor from here, all the vapor is being extracted and provided into the compressor. So the compressor receives all the vapor that we are producing. It compresses it so that it increases both its pressure and its temperature into superheated steam. The superheated steam is going to enter as our heating source. So we are using our own vapor after compressing it to be the source of heat in the unit. And this is why you do not need an external boiler, because the compressor is doing the work of having high temperature and high pressure steam coming in. This is our product. So it condenses here, and the condensate is basically going to preheat the feed, and then it will be collected as our final product here. It will go to the desalination water tank. So this is unique in that system, that you do not need any external sort of steam, but you are making your own heating steam by using this compressor. What is left here that we did not talk about in the figure is that the non-condensable gas is out, which means that we are using some sort of an ejector to create vacuum, and through the vacuum you are actually sucking out the non-condensable gases, carbon dioxide or so, and you are taking it out of the system. So is the system clear? You have any questions?
Yes, doctor, but one question.
Go ahead.
So when you extract the vapor and you insert it again to the compressor, this is what increase the efficiency and the productivity of the
The whole target was basically to make sure that we do not rely on external source of steam. That was the basic idea. Number one, the suction side of the compressor is going to create a little bit of lower pressure in the evaporator, and you need the lower pressure to improve the evaporation process, so you are getting a little bit more vapor. But the whole target is you are generating your own steam, and this is used as a heat source, and then when you condense it, it is your product.
Okay, so when you compress it, you basically increase the temperature, right?
Temperature and pressure. This is
this
vapor, and pressure and temperature are interrelated.
I see. So the pressure and the, okay, so the steam goes in as a high, very, very hot. Yani.
Not very hot. We are talking about a temperature again in the order of 65 degrees centigrade. So it's not superheated or highly superheated vapor, but according to the conditions that we have, to the running pressure that we have in the suction side, this is basically the kind of pressure that you need, so that you have a pressure with a saturation temperature of about 65 degrees centigrade. Why 65? Because this way we can protect our units against scaling, so that the lower the temperature of the seawater, the lower the potential of scale formation here. Did I answer your question, Ikhan?
All right. Thank you, Doctor. Thank you so much.
Okay, so we have compressor and evaporator. Ahmad, you have a question? I cannot hear you. There's something wrong with the sound. I think you can write whatever you want as a comment in the chat, because I cannot hear you.
Yes.
Yeah, go ahead. Sorry, I cannot hear you, Ahmed. There is something wrong with the sound. Please write down the question. There's something in the connectivity which is making this not clear.
Write it maybe in the chat. It's much better.
That's what I'm saying. Just write it down in the chat, and then I can get your question. Yes. Yeah, that's right. Khalid has written to you that your voice is not clear. We cannot really hear you or identify what you're saying. So you have the chat window where you can raise your question. You can write it in. Until Ahmad writes his question, we are talking about usually the compressor and the evaporator are brought together into a single unit. We'll see that in a figure in a while. We have seen it in the previous figure that I've shown here, that shows that they are basically one unit. This is the compressor here. I'm looking at the lower left figure. That's the compressor and that's the evaporator. So all of them are brought in one compartment, and that makes it easy to handle. You're just bringing one unit in. The evaporator has horizontal falling film tubes, and we have seen earlier, we discussed it earlier when we talked about evaporators, that this is better for high heat transfer coefficient. We have the nozzles to spray the water in. You have the tube to suck the vapor out, which is basically connected to an ejector, and there is a mist eliminator so that you can make sure that water droplets are not leaving with the vapor. The mist eliminator separates them, and then your vapor is pure. We're talking about a moderate investment cost. It's not very costly to acquire a unit like this. It is reliable, which means that it can operate for long period of time and operating with the production which is needed. Seawater intake and pre-treatment is simple. We're talking about heating water anyway. Horizontal falling film tubes are there. Low temperature operation, 60 to 65 would be the limit of the temperature for the sprayed seawater. And accordingly, you can have less scale formation in this unit accordingly with this. It is modular, which means that you can do it in a small size and a medium size. So far, there are no big sizes. By big, I mean tens of thousands of cubic meters. That does not exist. I think in UAE, there are a couple of units, and each one of them is like 5,000 cubic meter per day. And this is about the limit for this technology. You can adjust it simply to the load variations. Since you are talking about a compressor which is rotating, the speed can be controlled of the compressor, and then you can control the load accordingly. These are some comparisons with units that are existing in the literature. So in 1981, there is a unit that has been compared with RO. So far, I have to tell you that one of the drawbacks, one of the disadvantages of the mechanical vapor compression is that the power consumption is high. Look at these numbers. These numbers are old, by the way. We are talking about RO system that would require, RO is reverse osmosis. It requires about 4 kilowatt hour per cubic meter. If you read the article I just released this week on the Blackboard, you'll find that the latest reverse osmosis units that are installed in the kingdom currently are running at about 4 kilowatt hours per cubic meter. This is the design load, which means that when you put it on the ground, when you operate it, the load can be a little bit higher than that, depending on the kind of intake water that you are having. And this is for seawater, definitely. In comparison, you'll find that this power consumption for the mechanical vapor compression is 10 to 18 kilowatt hour per cubic meter. We are talking about maybe 2.5 to 4 times the power requirement. That's why the market share of the mechanical vapor compression is small. However, they are not sensitive to the quality of the seawater which is coming in, which is always an advantage of the thermal desalination systems compared to the reverse osmosis units. Since the reverse osmosis units are very sensitive to any change in the intake quality of the seawater which is used. However, currently or after that, maybe a decade later, the system performance has improved and dropped from 10 to 18 kilowatt hour per cubic meter to an average of 8. So that we're talking about something like close to 50% reduction, but yet it's still higher than the reverse osmosis, much higher than the multi-effect distillation system, higher than the RO system. And then talking about the size of the units producing up to 2,500 manufactured in 1985 with a compression ratio of about 1.3 or 1.85, depending on the number of effects that you have. In 1994, more than 200 units were operating, so multiple evaporators are there in the system. In 1995, the units were installed in Canary Island. They have operated for about 8 years, and they have shown a plant factor of about 87 to 90%. A plant factor means that how long during 1 year a unit has been operating, up and running. When you are talking about 90% operation, so it has been down for maintenance only 10% of the time. So if we are talking about like a 1 year, then 1 month for maintenance, and the rest is just the unit is up and operating 24/7. And this is some sort of a good performance indicator. And he was talking about, yes, that's because we are not worried too much about scaling, since temperature does not exceed 60 or 65 degrees centigrade. This is a layout of the unit, where basically what you have here is the blue thing on the top is basically the evaporator. And to the left is the vapor compression system, which is basically this. This is basically the compressor unit that we have. Seawater is coming following that green color here. So seawater is being taken. There is a seawater pump, intake feed pump, and the seawater is going, if you are following the red dot on the screen, this is the seawater coming here into a heat exchanger. Here we have single heat exchanger where we have 3 fluids. They are not mixed together, of course. One of them is the seawater in, this is the green one, and this is the one that needs to be heated from T cooling water. This is its initial incoming temperature to a value that we call T0. And in order to heat it up, who are using the brine, which is rejected, and the brine is the yellow line. The yellow line passes by the heat exchanger, so it is given off its heat to the seawater. The distillate, which is the blue line here, is also coming into through a product pump to water before the distillate goes into the distillate storage tank. So there's here it's not necessarily to be a single heat exchanger. Actually, our analysis we are going to do it as if they are two heat exchangers. One of them is between part of the seawater with the brine, the other is the rest of the seawater with the distillate. So this is not necessarily the kind of only alternative for the preheating of the feed. There's something interesting here in this figure, which is I just made this this addition today, looking at just showing here that the brine, which is leaving the unit, is recirculated back. The brine is leaving at saturation temperature, which is this here, right here. And then as it leaves down there, here it is mixing with the seawater. So you are bringing the seawater, you are mixing the seawater with the rejected brine. This is going to help in two things. Number one, increase the temperature of the seawater further. And the second thing is that you are recirculating the brine, you are adding seawater into it to reduce its salinity. So that reduced salinity is going here to be going through what we call a recirculation pump, and this is what is going to be sprayed here. Again, not all of the units are like that. Some of them does not have this kind of mixing, but it is just an idea for having higher temperature of the feed sprayed, and meanwhile you use some of the seawater to reduce the salinity of the rejected brine. And this is going to be sprayed in the unit here so that you are basically reducing the temperature difference between the feed and the saturation temperature inside. So that is basically some sort of a quick description of the unit. This is the temperature profile. The seawater leaves, gets into the evaporator after being heated in the two heat exchangers. So it enters at a temperature TF, feed temperature. Once it sprays on the outside surface of the tubes, the vapor inside the tubes, which is hot, is going to heat it from TF to the saturation temperature TB. It will remain at the value TB, where it is going to undergo the evaporation process. Evaporation occurs at a constant temperature. When it evaporates, the vapor that is going to leave is going to be at a temperature less than the saturation temperature by boiling point elevation. The vapor has to pass by the demister, so there is a reduction in pressure, which is associated with another reduction in temperature. We may, in our analysis for simplicity, neglect the delta T demister as we did previously in the previous systems, and only consider the boiling point elevation as a difference. Now, the vapor that has formed here is going to get into the compressor. The compressor is going to increase its pressure and temperature to this value. The temperature is going to leave the compressor as TS. This is temperature of the vapor that has been admitted into the compressor. It will enter inside the tubes. Are you able to hear me now? There was some sort of an instability in the voice due to the connection of the internet. I hope it's fine now.
Yes, it's clear.
Okay. And then the superheated vapor is going to leave the compressor at TS. It will enter into the tubes. It will cool down sensibly. It will lose its degree of superheat from TS to TD. And then it will start condensing. So the rest here will have a constant temperature because this is condensing vapor. The vapor leaves the unit, or the condensate leaves the unit, which is liquid actually at a temperature TD. And this is the TD that enters into the heat exchanger. It will cool down from TD to T naught. The brine is going to cool down from TB, saturation temperature, which is leaving at this location here. It will enter another heat exchanger to be cooled down from 2B to T naught. And both of these streams are going to heat the feed from T cooling water up to T feed. So this can be occurring in two heat exchangers, which is typically what we are going to consider. TD will cool down to T node, heating the seawater or part of the seawater from T cooling water to T feed, and another heat exchanger where basically the brine is cooled to the same temperature T node, heating the seawater or the rest of the seawater from T cooling water to T feed. So actually, what you see here in this figure was corresponding to the figure of the unit that you have seen in the previous slide. However, typically this is what we'll be doing in general. That is, we have a couple of heat exchangers. They are preheating the feed, and the feed is being preheated from T cooling water to TF by splitting it into heat exchanger. One of them where we use the distillate to preheat the seawater, so the distillate cools to this temperature. And here again, for simplicity of analysis, in the other heat exchanger, you assume the brine is also cooled down to the same temperature T node, and it will heat the rest of the feed from T cooling water to TF. So this is basically a quick description of the unit and the benefits of the units, the kind of advantages that we are getting from this unit. The disadvantages are basically the relatively high power consumption. We are talking about at the best condition of 8 kilowatt hour per cubic meter, which is at least twice what you can get in a reverse osmosis right now. It is also twice what you can get in a multiple effect desalination system operating with steam. So relatively speaking, we are talking about higher energy consumption. On the other hand, the benefits is that it's a standalone unit. You can take it and operate it any location, even if it's not connected to the electric grid. All you need is just either a wind turbine or a diesel engine to run the compressor, and then you are up and running there. Some of the design requirements for best performance are given here, that the degree of superheat is somewhere between 4 and 10 degrees centigrade. Here I'm talking about the difference between this TS and TD. This superheat is somewhere between 4 and 10 degrees centigrade. You don't need to increase it much, because if you increase it, then you are going to require higher power of the compressor, and that's not really something that we're already suffering from high power consumption. You don't want to increase it more. The differences between the feed and the brine is 1 to 5 degrees centigrade. I'm talking about this increase in temperature. You better heat the feed to the best or highest temperature possible in the heat exchangers. On the other hand, you don't want the heat exchanger size to be infinitely large. So what you do is you make a compromise, a balance between the size of the heat exchangers and the temperature of the feed, so that it would be less than the saturation temperature by 1 to 5 degrees centigrade. 5 was typically what we used in the previous system, in the single effect evaporation and single effect evaporation with vapor compression. The difference between TD and TB, again, is somewhere between 1 to 5 degrees centigrade. What we are talking about here is basically this difference between TD and TB, the temperature difference between the vapor which is passing inside the tubes and the seawater which is sprayed outside the tubes. So this difference is again in the order of 5 or 1 to 5 degrees centigrade. Finally, the temperature difference in the preheaters, in the feed preheaters here, it's 5 degrees centigrade. And the 5 degrees centigrade maximum here is made such a way that the size of the heat exchangers is acceptable, so that they are not too large. And if they are too large, then it will be very expensive, and that's not what we're looking for. Maintaining these temperature differences within that range is going to keep the compressor power consumption within practical limits, something which is affordable, avoid excessive increase in the heat transfer area of the evaporator as well as in the heat exchanger. Remember, this unit does not have a separate condenser because we condense our product, which is the vapor, inside the evaporator. The vapor is heated to superheated condition. It gets into the evaporator where it will lose the superheat and condense into a product. And this is one of the beautiful aspects in this unit. I'm not going to get into the energy balance equations. I'll keep it to our next class and have it along with a numerical example. So I'm going to stop here, and I think it will be time to look at the quiz at this moment. So if you get to the blackboard, the quiz must have been released to you now. So you should be able to see it. I hope you can.